All right, let's dive in. We're going to tackle a question that sounds incredibly simple, but the answer completely upended all of physics. Is the universe smooth and continuous, like a painting? Or if you could zoom in, way in, would you find that reality is actually pixelated? This is the story of quantization, the incredible discovery that at the very bottom, our world is made of tiny, individual chunks. For the longest time, physicists were pretty sure they had the answer. Reality is smooth. It's like a liquid. You can have any amount of something, energy, speed, you name it. But there were these nagging little problems, these experimental results that just didn't make sense. And they forced scientists to consider an alternative that, at the time, sounded completely nuts. And this right here is the perfect way to picture it. The old classical view saw the universe as a smooth ramp. You can stand anywhere you want on it. But the quantum view says, nope, it's more like a staircase. You can be on the first step or the second step, but you can never, ever be in between the steps. That right there is the essence of quantization. Now, the funny thing is, this idea of a pixelated reality wasn't totally new. The roots of this thinking actually go way back, all the way to ancient Greece, with the most basic thing of all, matter itself. Way back in 450 BC, a Greek philosopher named Democritus had this wild idea. He thought, what if you keep cutting something in half? Eventually, you'd get to a piece so small you couldn't cut it anymore. He called this an atom. For thousands of years, it was just a cool thought experiment. But by 1900, the evidence was in. It wasn't just a theory anymore. The world really was made of atoms. So there it was. The first pixel of our universe had been identified. Okay, so matter's grainy, got it. But the story didn't stop there. The rabbit hole goes deeper. The next big shocker was that it wasn't just stuff that was pixelated. The very essence of electricity, electric charge, also comes in discrete little packets. So in 1897, you've got this physicist, J.J. Thomson, and he's messing around with these weird beams called cathode rays, and he makes this stunning discovery. The rays were made of tiny negatively charged particles. But here's the really revolutionary part. It didn't matter what materials he used in his experiment, he always got the exact same particle. The conclusion was just inescapable. These particles, what we now call electrons, were a fundamental building block of, well, everything. But the real slam dunk proof came in 1909 from Robert Millikan's brilliant oil drop experiment. Basically, he zapped these tiny oil drops with charge and then floated them in mid-air using an electric field. This let him measure their charge with incredible accuracy. And what he found was just mind-blowing. The charge on any drop was always a whole number multiple of one single fundamental amount. Charge wasn't some smooth fluid. No way. It was like cash. It only came in identical coins. All right, so matter is quantized. Check. Electric charge is quantized. Check. But the next piece of the puzzle, oh man, this is where classical physics just completely fell apart. And it all started with a really simple question. Why do hot objects glow? Now, you'd think this would be easy, right? Classical physics had a perfectly logical answer. The atoms in a hot object jiggle around, and jiggling charges create light. Simple enough. The problem was when physicists actually did the math using their trusted equations, the answers were just spectacularly wrong. The theory predicted that a hot object should be blasting out an infinite amount of energy, which, it clearly doesn't. And, look at the difference here. The bar on the left is what we actually measure in a lab. A nice, sensible, predictable curve. The bar on the right, that's what the old theory predicted. It just shoots off the charts towards infinity, especially in the higher energy ultraviolet part of the spectrum. They weren't kidding when they called it the ultraviolet catastrophe. It was a total disaster for physics. So, in 1900, a German physicist named Max Planck came up with a solution. He later admitted it was an act of desperation, but it worked perfectly. He very reluctantly proposed that maybe the vibrating atoms inside a hot object couldn't just have any old amount of energy. Instead, what if their energy had to come in discrete steps, like multiples of some basic minimum-sized energy packet? Planck called this minimum energy packet a quantum. And he discovered that its size was tied directly to the frequency of the light, connected by this brand new fundamental number of the universe, h, which we now call Planck's constant. And with just that one radical assumption, that energy is quantized, poof, the ultraviolet catastrophe completely vanished. The theories suddenly matched reality perfectly. But here's the thing, even Planck thought this was just a weird mathematical trick, Something funny about how atoms vibrate. It took a young patent clerk named Albert Einstein in his unbelievable miracle year of 1905 to take it a giant leap further. He said, hold on, what if it's not the atoms that are quantized? What if the light itself is chunky? Einstein was looking at another stubborn puzzle, the photoelectric effect. That's just when light shines on a metal and kicks out electrons. But the classical wave theory of light could not explain three really bizarre facts about it. First, the energy of the electrons depended on the light's color, its frequency, not how bright it was. Second, some colors of light did absolutely nothing, no matter how intense you made them. And third, it all happened instantly, with zero time delay. Einstein's solution was just breathtakingly elegant. He took Planck's idea and ran with it. What if light isn't a continuous wave, but a stream of tiny energy packets, like little light bullets? We now call these photons. And he proposed that the energy of each individual photon was decided by its frequency, using Planck's exact same formula, E equals hf. And this one simple idea just clicks everything into place. An electron gets hit by one single photon, which dumps all its energy at once. That's why there's no time delay. The photon's energy is all about its frequency, its color, which is why color matters, not brightness. More brightness just means more photons, not more powerful ones. And hey, if a single photon doesn't have enough energy to knock the electron loose, well, then nothing happens. Every single mystery, solved. Now, the photon was a beautiful idea, but it was so radical that a lot of physicists, even Millikan, were really skeptical. They needed one final, undeniable piece of proof that nobody could argue with. And that proof came in 1923 from Arthur Compton. He set up this brilliant test. He said, look, if photons are really particles, they should act like them. If you shoot a photon at an electron, it should be just like one billiard ball hitting another. It should be a tiny cosmic game of pool. Now, it's really important to see how this is different from the photoelectric effect. In that case, the photon gets completely absorbed. It vanishes. But in Compton's experiment, the photon was expected to scatter, to bounce off the electron, lose a little energy, and keep on going. And that is exactly what he found. The scattered photons came out with less energy. The electron recoiled at precisely the angle and speed that the laws of a simple collision predicted. The results were a perfect match. It was undeniable. The photon was real. And just like that, the revolution was complete. Physicists were forced to throw out the old, smooth view of the universe and accept this new, pixelated reality. Matter comes in discrete atoms. Electric charge comes in fundamental units. And even energy itself comes in discrete packets called quanta. The smooth, continuous ramp of classical physics was replaced by the quantum staircase. This discovery didn't just solve a few problems. It threw the doors wide open to the bizarre, wonderful, and mind-bending world of quantum mechanics. And it leaves us with this profound question. If something as fundamental as energy is pixelated, what else about our reality is not what it seems?